everyone, and thank you for joining the inaugural APN Digital Summit. We have put this APN Digital Summit together to help our APN partner community to learn some of the AWS services that we feel our partners can make a strong impact to AWS customers. The services you will learn about today will enable you to transform your business and innovate on behalf of customers to better meet the business needs at a significantly lower cost. Feel free to attend as many sessions as you want. We have 20 sessions running over the course of 4 hours. Once you register for a session, listen in as we dive into the content. We will be sending out an email communication for each track with in-depth resources and trainings for you to continue your education within these service areas. We will also be sending you a survey link after the presentation. This gives you the opportunity to provide feedback so we can grow this series for our partner community. We also provide the opportunity for you to tell us what content and services you would like to learn more about so we can help shape the direction of this APN Digital Summit and what we host in the future. A few housekeeping items before we get started. First, the session is being recorded. We will send you the recording when this presentation is over, along with the additional information I just mentioned to help you continue to learn more about these services. If you have questions during the presentation, please feel free to ask them in the question window. We will do our best to answer all the questions as they come in, but if we don't, we will follow up in an email after. If you are having any audio issues, please try your computer's mic and speakers. This often fixes any problems that you may have. Thank you again for your time today. I hope you enjoy the sessions we have for you, and we look forward to hearing what you think. Now, I'm going to hand it over to our presenter.
Well, welcome to Dive into Amazon Elastic File System. My name is Daryl Osborne, and I'm a solutions architect with Amazon File Services. In today's session, we have structured it into 4 different phases. The first phase will be unveiling Amazon EFS and give you a foundation of what that service is and how it could fit into the services that you provide. The second phase will be around testing and optimizing the EFS and your application to take advantage of the EFS service. Phase 3, we'll talk about ingest, how to ingest your data into an Amazon EFS file system. And then phase 4, we'll talk about what does it take to actually run a file system and what's involved. So with that said, let's go ahead and dive right in. So we generally see 3 types of storage when we're talking about storage solutions. We want to identify what those 3 types are. We also want to take a look at some of the performance and features that you typically look at when you're choosing a different storage platform. And then, of course, we want to take a look at the economics. You know, what is the TCO? How much is this going to be costing you? So when we first start off, we want to talk about the 3 different types of storage. And typically we break that down into file, block, and object. So with a file system, data is typically stored natively as files in a hierarchical data structure. So each file and directory has particular data, metadata associated with it. And this metadata could be something like owner or maybe creation time. So in the enterprise, typically we see this as data stored that is accessible over the network by multiple clients at the same time. So when you think of file storage in the cloud, you can think of it kind of like a network attached storage appliance or service. The next type of storage we have is what we call block storage. And you know, if you have a set of disks, usually it's locally attached, and this is typically associated with a single computer. So in this, with this type of storage, data is stored in chunks, and these are called blocks. Now, operating systems will work with block storage by presenting it to the file system in a format that users and applications can use. But the underlying raw data is actually being stored as blocks. So you can think of block storage as locally attached disks. Then last but not least, we have object storage. Now here, data is stored in containers called objects. And this is defined, these objects are defined and identified by a unique key that is stored, without any type of hierarchy. It's really a flat system. And these objects are typically, you provide access to these objects using a simple API call. So you do either a get or a put. And it's all based on the key of that object. And this API is typically accessed over the internet. So why is file storage then so popular when we have three different types of storage platforms? For one, it works natively with operating systems. So operating systems are designed around file storage. File systems, are the abstraction used to display data to the end user. And these operating systems use file APIs to allow applications and users to read and write data. Next, it provides shared access while also providing consistency guarantees and locking functionality. And this is important. This is very somewhat unique when we take a look at the other storage platforms. So these characteristics are super helpful when you have distributed applications, when multiple clients are trying to read and write data at the same time and the same data set. But lastly, it also provides a hierarchical namespace. And this is very helpful because naturally, this is the way that we like to organize data. So another aspect to consider when you're deciding on what storage platform to use is how they compare to each other in terms of throughput and latency. And here on the x-axis, we have latency, and on the y-axis, we have throughput. So block stores generally provide the lowest latency. They don't though scale to the amount of throughput that's achievable by, say, file systems and object store, because typically block is associated with, say, a single server. There are some examples of workloads that require lower latency and relatively low amounts of throughput. Could be database applications or maybe even boot volumes. So when we think of block storage in the cloud, specifically in AWS, we think of EBS. So moving to the right, we take a look at file storage. And generally, this is used for and designed for low consistent latency. When you need, tens of gigabytes or gigabytes of per second throughput. And then as we continue to go to the right, we have object. And then this really provides the highest level of throughput and scalability. But it isn't designed for latency sensitive applications. So as we look here, we see sort of file storage is right in the middle. It has lower latency than object, but it has higher throughput than block. And because it is accessible by multiple clients at the same time, it's really a good fit for a variety, really a wide spectrum of use cases and workloads out there. So before Amazon EFS came around, we launched EFS just over 2 years ago. Customers would have to do it themselves. So they would have to spin up their own environment and provide a file storage to other clients. So in this environment, what they would have to do is spin up an EC2 instance. That would be a file server. They would have to manage that instance, manage the operating system, and manage the file server software. They would mount EBS volumes to it. And then they would be able to mount this from multiple clients. Well, in order to improve the availability and durability of this data, typically what they would have to do is spin up another EC2 instance in another availability zone. Again, mount multiple EBS volumes to that EC2 instance. Manage the software, the file system software, manage the operating system, and then manage a replication mechanism to replicate data from one file server to another file server. So as you can see, this can become somewhat complex. when you're trying to do it yourself. And just because you need to manage both the compute side of the file server system as well as the storage side, those storage volumes. And then you need to make sure that all of your clients are going to be able to access and mount the file system. So as you can see, there are a number of components that you would have to do if you're trying to do it yourself. Well, luckily, Amazon EFS came around, and Amazon EFS is a fully managed service. So it makes it very easy to set up and scale file storage in the Amazon cloud. So with a few clicks in the AWS Management Console, you can create a file system that is accessible to multiple Amazon EC2 instances via file system interface or file system semantics. And it supports a full, the full file system semantics, strong consistency, file locking, anything that you would expect out of a NFS v4 file system, you have with Amazon EFS. So when we designed EFS, our core tenets were around simplicity. So since EFS is a fully managed service, there's no hardware, there's no networking, there's no file layer to manage, and with just a few clicks, you're able to create a scalable file system. So it's very simple to set up and maintain and run. We also wanted to make sure that the pricing model was simple as well. So it's a very simple pricing model, and we'll talk about that a little later. One of the other core tenets with EFS is elasticity. So file systems automatically grow and shrink as you add and remove files. So there's no need to provision storage capacity or performance. You only pay for the storage space that you use with no minimum fees. And the third core tenet is scalability. So EFS file systems can grow to petabytes of capacity, and the throughput of the file system can drive, it scales automatically. So as you add more data to the file system, your throughput is able to increase as well. And you receive these benefits, these throughput and scalability benefits, while still providing consistent low latency access to the file system. So you can mount a file system from one client or thousands of clients and get the same low latency access to that data. Now, all of this is based and built on a foundation of high durability and high availability. So to change gears a little bit, let's talk about performance mode. So the default performance mode is what we call general purpose, and this is recommended for the majority of the workloads out there. It has the lowest latency of the two different performance modes that we offer, and it is really a perfect fit for the majority of applications that need a network shared file system. The other performance mode that we offer, we call Max IO, and this is recommended for scale out workloads when you need to access the data set or the file systems from hundreds or thousands of instances. And when we take a look at and compare the two performance mode file systems, we want to identify, well, when is one used versus the other? So for general purpose mode file systems, they're really designed for latency sensitive applications and general purpose workloads, while Max IO are designed for those scale out data heavy applications. Some of the advantages of general purpose mode file systems is that they have the lowest latency for file system operations. While the advantage of Max IO, you virtually have an unlimited the ability to scale out throughput and IOP. So it continues to grow and grow. Some of the trade-offs is that general purpose mode file systems has a limit of 7,000 file system operations per second, while the Max IO doesn't. But it does come with a cost of slightly higher latency. So Max IO file systems have slightly higher latency than general purpose, but they do not have the 7,000 file system operations per second limit that general purpose mode file system. So again, you sort of have to balance what does your application or your workload need and that will help determine which file system performance mode you want to use. We do recommend starting out with general purpose mode file systems to see if your application performs well with that. But if you see that you need and you're starting to hit that limit of 7,000 file system operations per second, then we would recommend you move over to a max IO file system. So as I mentioned earlier, when to use general purpose, it's really the best for most workloads. But when you need to scale out, max IO is definitely the way to go. Now, we also have different throughput modes as well. So the default throughput mode is what we call bursting throughput mode, and that's recommended for the majority of workloads. And that's designed for bursting or burstable workloads. When for a short period of time, you need to burst to high levels of throughput, then for the rest of the time, you can sort of maintain a low level of throughput to your application or to your file system. The other throughput mode we offer is what we call provision throughput mode, and that is recommended for higher throughput to storage ratio workloads. So if you require more throughput than what is provided in bursting throughput mode, then we would recommend that you switch your file system over to provision throughput mode. So here we can also take a look at and compare the differences between the two. So when do you want to use bursting versus provisioned? So bursting throughput mode, it's really good for a varying throughput workload. So again, these bursty applications that require higher levels of throughput for short periods of time, bursting throughput mode is really the way to go. If you need a higher consistent throughput where you don't have a lot of data that you're going to be storing, then we recommend looking at provision throughput mode. Some of the advantages, definitely with bursting throughput mode, it is auto scaling. So as you add more and more data, your throughput also increases and you're able to burst at double the baseline throughput for short periods of time. So it is definitely an advantage when you continue to add more and more data. The advantage of provision throughput mode that it is user definable. So you set the throughput that you need independent of the amount of data you have stored in your file system. Some of the trade-offs, there is a fixed throughput to storage ratio with bursting throughput mode, and that's 50 megabytes per second per terabyte of data stored for the baseline, but you're able to double that and burst at 100 megabytes per second per terabyte of data stored. While with provision throughput mode, there is a separate charge for the throughput that you provision above what's available in the bursting throughput mode, and we'll dive deeper into this in a few minutes. So when to use one versus the other. So again, we recommend starting out with bursting throughput mode. That's really recommended for the majority of the workloads out there. But if you do have a workload that requires higher throughput than what is provided with bursting throughput mode, or you need to ingest a lot of data very quickly when you're first starting out, then we would have you consider using a provision throughput file system. So let's talk a little bit more about provision throughput mode. This is the throughput mode that where you set the throughput amount of data that we have stored in the file system. So here you're able to set that regardless of how much data you have. You can increase it as often as you need, and you can switch between throughput modes or decrease the amount of throughput you have provisioned as long as it's been more than 24 hours since the last time you decreased or you switched throughput modes. So when we talk about security, there are a number of features available to these file systems, irregardless of what performance mode or throughput mode being used. So to control access to your file system at the network layer, file systems you gain access to a file system through an endpoint. These endpoints show up in your VPC as an ENI, an elastic network interface. And you have the standard VPC security controls around an ENI as you would any ENI in your VPC. So specifically security groups and network ACLs. So this is how you would identify what other security groups, IP addresses, or CIDR blocks will have network access to that to your file system. In terms of controlling access to file and directory data, we support POSIX permissions. So if you're familiar with how POSIX permissions works today in terms of granting users and groups access to individual files and groups, you're going to feel right at home using Amazon EFS. So when you're talking about controlling API access to manage and administer the file system, we integrate with AWS IAM, or Identity and Access Management. And here we have action level and resource level permissions. So you can identify which IAM user within your AWS account will have permissions to create file systems, delete file systems, manage the security groups on what security group or IP addresses or CIDR blocks will have access to that file system. It will also you can associate permissions on tagging file systems for cost allocation reasons and things like that. So all of that is done through IAM. So we fully integrate with IAM. Encryption is very important, definitely when it comes to security. Security is our #1 priority. So we do offer encryption of data at rest and in transit. So when you create a file system, you can identify if that file system will have encryption of data at rest enabled. You can also select the CMK, or the customer master key, that is used to help encrypt that data at rest. You can also enable encryption of data in transit when you mount the file system using our EFS mount helper. We'll go into a little more details later in the session. And if you require external compliance, regulations, or you need to follow those, we are HIPAA eligible and BAA, and we are PCI compliant as well. So if you have any of those compliance needs, then Amazon EFS will satisfy those for you. So today, Amazon EFS is available in 10 regions. And we continue to look and are moving quickly to move to other regions throughout the world. So in terms of EFS economics, there are no minimum commitments or upfront fees. And since it's a fully managed service, there's no hardware to manage, so there's no storage, and it automatically grows and shrinks as you add and remove files. So there are no other fees, charges, or billing dimensions. There are no request charges like other storage services. It's a simple price per gigabyte per month, and because our costs vary from region to region, so does the price vary from region to region as well. So let's talk about the different pricing dimensions based on the throughput mode of your file system. So if you're running in bursting throughput mode, there is a single pricing dimension. Basically, you pay only for the amount of storage that you use, and included in that price, you actually receive 50 kilobytes per second throughput per gigabyte of data stored. So there is an aspect of throughput associated with the storage that you're paying for, and that's included in the bursting throughput mode. Now, when we talk about provision throughput mode, there actually are two pricing dimensions. So there is a storage pricing dimension, and there's also a throughput pricing dimension. And in the throughput pricing dimension, you actually pay for the amount of throughput you provision above what's available in the throughput included in the storage price. So as I mentioned, the storage price includes 50 kilobytes per second of throughput per gigabyte of data stored. So you would only pay for the amount of throughput you provision above that. So again, this is going to vary depending on how much data you actually have stored in your file system. So with provision throughput mode, there are two pricing dimensions. So really, when we go back and take a look at this diagram again, we see that if you try to do it yourself, there are Amazon EC2 instance costs associated with it on the EC2 instances for the two file servers we show here. There's also going to be costs associated with the Amazon EBS volumes that you're going to be mounting to these EC2 instances. And then there's also inter-AZ data transfer costs when you're replicating data between these two file servers. So when you look at that, it really adds up. So typically we see that Amazon EFS is roughly 70% less than if you wanted to do it yourself. And we can see here that when you add up the storage, the compute, and the transfer costs associated with in this example, just a 500 gigabyte, or here we're actually provisioning 600 gigabytes of storage, of EBS storage, we see that that would add up to roughly $540 per month. With that same amount using Amazon EFS, that would only come out to $150 per month. So you do see the economics of and the benefits of running an Amazon EFS file system versus trying to do it yourself. And this doesn't include some of those other costs associated with maintaining all of those resources if you tried to do it yourself. So Amazon EFS is designed for a wide spectrum of use cases and workloads. So anywhere from highly parallelized scale-out jobs where workloads will require some of the highest possible throughput. Some of those would be big data applications or media workflows, all the way to single-threaded latent-sensitive workloads, and really everything in between. So we see a number of customers using EFS today, and here's just a list of a few. So you don't have to take my word for it. These customers are running EFS today, anywhere from using it for database backups to media transcoding applications and workloads, to web serving and content management, and as well as container storage and big data and analytics workloads. So we have a large spectrum of customers today using Amazon EFS. So now that we've done an overview of EFS, let's really talk about testing and optimizing your application to take advantage of EFS, and what we can do on the EFS side to optimize it for your workload. So when you're thinking about testing and optimizing an application, what do you typically think about? So it's really the solution architecture. What is the solution? What am I trying to architect for? What is the workload? What is the application? Next, you want to talk and think about functional testing. Can my application functionally work with Amazon EFS? Does it satisfy all of those requirements? And lastly, we want to look at performance testing and optimization. How can I tune my application to best leverage this data storage design that EFS offers? And then what knobs can I turn on EFS to tune it to help my application and my workload? So let me give you a brief overview of what the EFS architecture is. So when you create a file system, you actually create that file system within an AWS region. You don't create it within a VPC. You don't create it within an availability zone. You create it within a region. But then your clients that access this file system, they are coming from a VPC. So you would create a VPC. This VPC would span multiple availability zones. And then you would have your NFS clients or your EC2 instances in these availability zones that want to access this file system. So you would also create what we call mount targets. And mount targets is an EFS construct. You create one mount target per availability zone, and these act as endpoints. And this is, earlier I mentioned these endpoints. These show up in your VPC as an ENI, an elastic network interface. And this is where you would control access to your file system using the standard security mechanisms like network ACLs and VPC security groups. We also create a DNS name, basically this file system ID. And this file system ID or DNS name you would use to mount the file system um, on your EC2 instances. And this is the mechanism that you would use to get access to the file system from your NFS clients running in EC2. So there are no single points of failure when we look at these engineering constructs that we have built for EFS. So when you take a look at the DNS name or the mount targets or the file system, that storage platform itself, they're all engineered for high availability. So there are no single points of failure. So you can rest assured that your data is going to be accessible and it's going to be available to you when you need it. So how do you test EFS? So really it's as simple as 1, 2, 3. You create a file system. This can take just really a matter of seconds, or maybe it's really a matter of seconds, either through the console or through some API or CLI calls. Once that file system is created, you would also create mount targets. Again, one mount target in each availability zone within that VPC. And then once that is created, then you just go ahead and mount the file system from your EC2 instances. And now you have access to it. So it's very simple and easy to maintain and manage a file system. There are only a handful of APIs that we expose because it is a fully managed service. There's really not much to do. So we do have APIs to create a file system and manage the mount targets associated with it. Tagging a file system so you can have cost allocations associated with it, managing the file system in terms of changing the throughput mode from bursting throughput mode to provision throughput mode, viewing the details or describing the file system, and of course deleting the file system and deleting some of those components. So it is very simple and easy to manage and administer a file system. So some of the best practices we have when using an EFS file system are this. So we do recommend using Linux kernel 4 and above on the clients where you're mounting the file system. So there are a number of reasons, and sometimes I do get asked, well, how important is it? If I'm running an older kernel version, say I'm running kernel version 3.14, how important is it to actually move over to the latest kernel version, maybe 4.14 or at least 4 and above? And what I could do is sort of demonstrate what that would look like. So here I recorded a video of 2 EC2 instances. One's running Linux kernel 3.14, the other is running Linux kernel 4.14, and we have the exact same file system mounted to it. I just want to verify that these 2 instances have the kernel that I mentioned. And what we want to do is just verify that the same file system is mounted and how they're mounted. So each file system is mounted and they're all mounted using NFS 4.1. Now what I'm going to do is run small file to generate 1,024 files and see how fast I can do that. So with the 4.14 version, kernel version, I can generate that in roughly 2.5 seconds. While with 3.14, it took a little over 8 seconds. Again, this isn't specific to EFS. This is more specific around the kernel. There are some operations that the kernel cannot execute in parallel, even though the application is executing those in parallel. So again, there are some performance benefits using a current kernel version than some of the older kernel versions. So that's one of the reasons why we recommend using Linux kernel 4 and above. Another recommendation we have is using our EFS mount helper. So we have released an EFS mount helper, and that is a wrapper to execute an NFS mount using our recommended mount options. So we want to mount using NFS protocol 4.1. And there are some other mount options that we recommend that you use. And all of this is built into this EFS mount helper, which is a wrapper that will execute this for you. It's a very simple command, as you can see here. The bottom command is the command when mounting using the EFS mount helper. You can also use the EFS mount helper to mount and have an encrypted connection. So you can enable encryption of data in transit. where it will create a TLS connection between this instance and the EFS file system. So then all of your NFS traffic will be encrypted and sent over this encrypted tunnel. But we do recommend using the EFS mount helper. And if you can't do that, then we still recommend mounting using NFS Client 4.1. The EFS mount helper is available in the Amazon repository. So it's a simple, if you're running Amazon Linux, it's a simple yum install. If you're running other Linux distributions, it's available as an open source project on GitHub. So just like the kernel version, I do have customers that ask me, well, how important is it? If I'm running, 4.0 versus 4.1, how important is it? What type of difference is that going to make when I'm trying to access it? So let's go ahead and run a very similar test, really the same test, but I have two different instances here. I'll just show you here that both are running the same kernel version, 4.14. The top one is going to be running NFS Client 4.0, while the bottom instance is going to be running NFS Client 4.1. We're going to run the exact same small file, generating 1,024 files using 32 threads, so it's in parallel. And we see that the NFS 4.1 is able to execute that in 2.5 seconds, while the NFS 4.0 executes that in 8.3 seconds. Again, there are certain operations, in this example, open and close operations, when executed in parallel by the application, will be serialized when you mounted the file system using NFS 4.0. If you're mounted using NFS 4.1, those operations will be executed in parallel. So again, you take advantage of the parallel design, this distributed data storage design that EFS offers when you access the file system in parallel. So you want to use those tools that allow you to do so. So Linux kernel 4 and above, as well as NFS client 4.1. So EFS is POSIX compliant, and it is compliant with NFS 4.0 and 4.1. But again, even if your application does currently run on in using NFS 4, we do recommend that you test. So I always like to say test your application to make sure that it runs great against Amazon EFS. So typically what we see customers do is run a few throughput and IOPS tests to see how their application runs against EFS. So let's go ahead and jump over to my terminal, and we'll run through a couple of tests. So here's some scripts that I'm going to be running, and here's my screen. So right now we see that we do have a file system mounted to this EC2 instance. It's mounted as MNT EFS01. So what we want to do is run through just a few examples. So the first throughput test we're going to do is what we call, we're going to be using DD. So we're going to generate a 2 gig file as fast as we can. The block size I've identified is 1 meg. And I'm doing a sync at the end of the 2 gig file. So we're saying, okay, I'm going to write a 2 gig file. I'm going to do a sync of data and metadata at the end of the 2 gig file. And I'm using a 1 meg block. And we see that we can get 205 megabytes per second throughput when using this. Now, this isn't that realistic in the sense that a lot of times we do sync operations more frequently than at the end of each file, specifically if they're very large, like a 2 gig file. So we'd want to do more frequent syncs to make sure that the data is persisted to disk at a more frequent basis. So if we actually change this command and said, well, let's go ahead and do a sync of the data and metadata after the end of each block. And I did that by changing the O flag equals sync option. And we can see here that, it's already taking us 12 seconds. And we're only at about 330 megabytes. While in the previous example, it took us only 10.5 seconds to write 2 gigs. And we can see that we're only getting around 25 megabytes per second throughput. So what's the difference here? What happened? So, this is a single threaded application. So what we're doing here with this DD command is we're writing a 1 meg block, then we're issuing a sync command. So we're making sure that 1 meg block is persisted to disk, both data and metadata. And then we're moving on to the next 1 meg block. So there's a lot of network back and forth going on, making sure that this data is persisted to the disk. So with all of these network operations, there's latency involved in these. So that sort of adds to the time, which then reduces the amount of throughput we're able to achieve. And as we can see here, we're only, we're up to maybe 25.3 megabytes per second. We're at 73 seconds, and we still haven't completed the 2 gig file. So we wait a couple more seconds. I would say around 85 seconds, we'll probably be finished the 2 gig file. So here we are, about 84 seconds, and we completed it. So a big difference by just changing one option in our operation. So you need to look at your application and try to figure out, how does my application write data to NFS or to EFS in this example? Am I doing a sync at the end of each block, or am I doing a sync at the end of each file? Because again, a very chatty operations, network operations, you're going to have higher levels of latency because of all these network operations, and you're going to have lower throughput. Well, what if we change this up a little bit and said, you know what, instead of doing a sync at the end of, well, we'll still do a sync at the end of each block, but if we increase the size of the block, what would happen? So as we can see here, we changed the block size from 1 meg to 16 meg. And now our throughput, we're up to 93 megabytes per second. So again, a big difference by just changing the block size and the amount of data we're sending through the pipe before we do a sync. So less frequent sync operations can improve the throughput to your file system. And in this example, we're able to write 2.1 gigabytes of data in only 23 seconds. Well, let's continue, and I like to do another what if scenario. So what if we went back to a 1 meg block size? We know that it's going to take roughly 85 seconds to do. But if instead of writing it in serially, basically having one thread write 2 gigs of data, what if we had 4 threads writing in parallel, each thread writing 512 megabytes of data? So in this example, I'm using New Parallel. New Parallel is an open source tool that allows you to run commands in parallel. So here I've got 4 jobs or 4 threads. Each thread is writing 512 megabytes of data. The block size is still one meg, and I still have this sync command basically saying I want to sync at the end of each 1 meg block. So if we did this with 1 thread writing 2 gigs, we know it would take 85 seconds. Now, by using 4 threads and running those 4 threads in parallel, we're able to cut that down to 21 seconds. So again, this just shows another example of how by parallelizing your workload to EFS, you're able to increase the throughput to your file system. Well, what if we combined the two? What if we said, you know what, let's go ahead and have 4 threads, but we're going to also use a larger block size of 16 megs. Now, how will that improve the performance to EFS? So now we're able to get that down to just under 9 seconds. So again, a great advantage if we can combine and aggregate your I/O to have larger I/O size, reduce the number of sync operations, and have more threads running in parallel. You're able to then improve the throughput to your file system. Sometimes though, you may not be able to change the size of the I/O, but you can add more, hopefully you can add more threads. So in this example, we went back to a 1 meg block size, but instead of 4 threads, we have 16 threads. And now we'll see how fast, using 16 threads, we're able to write 2 gigs of data. And again, we're down to 8 seconds. So you're roughly, 250 megabytes a second to this file system, while before we were only able to achieve maybe 205 megabytes a second, and much slower if you were using a single thread. So that is the sort of the throughput test, and I do have customers running IOPS test against EFS as well. And they run something similar to this. I've seen this written using a number of different languages. But what this is basically it's a simple touch command where I want to generate 1024 0-byte files to EFS. And I'm going to go ahead and kick this off. I just started it. And, we're going to sit here and we're going to wait. And we're going to wait. And we're going to wait a little longer. And this is a single threaded operation. So we know it's going to take some time. So we'll round up. It took us 18 seconds to write 1024, create 1024 0-byte files. So to me, that seems long, and I'm sure it is to you. Well, why did it take so long? Well, again, there's a lot of metadata operations going on, and because this is single threaded, and it's writing out to this massively distributed file system where your data is durably stored across multiple storage nodes in multiple availability zones, there is latency associated with those types of operations. And because EFS is built on high availability and high durability, we wanted to make sure before we return the success back to the application, we wanted to make sure that that data is durably stored across multiple availability zones. So that took a long time. Well, what if we compared this to, say, EBS? So I actually have a command here where I'm doing the exact same command, writing to an EBS file system. I've got an EBS volume mounted to this instance, and we can see that we can generate 1024 files in just a little over 3 seconds. So a big difference: 18 seconds, 3 seconds. Well, from our throughput test, we know that by using multiple threads in parallel, we're able to achieve higher levels of throughput. So maybe we could do the same with IOPS. So let's go ahead and rewrite that command. And now we're going to use 32 threads to generate 1024 files. So again, we're using new parallel. And we have 32 threads or 32 jobs running in parallel. Each job is going to write 32 files. So we see that we've been able to reduce that from 18 seconds down to 10 seconds. Well, definitely that's an improvement, but it's still much higher and slower than what we're able to do against EBS. Well, again, what can we do? So some of you may be familiar with Linux file systems, specifically NFS, and there's this concept of inodes. And inode is metadata associated with file system objects. So that could be a file or a directory. And when you're trying to do a lot of operations against a single directory in parallel, you could experience inode contention when you're having a lot of operations and the inode is trying to take and receive all of these operations and get up to date. So what if we rewrote this and said, you know what, I don't want to write all of my files into a single directory. I want to spread these out to different directories or subdirectories or different inodes. So let's do that. So in this example, what we're going to do is we wrote 32 files. We had 32 threads writing 32 files in parallel, each thread writing to a different directory. And we can see that now we're able to generate 1024 files in just over 1 second, even faster than the EBS example. So again, by taking advantage of the distributed data storage design of EFS and accessing that using multiple threads and understanding sort of this concept of inode contention and knowing that, you know what, if I can spread this across more subdirectories when I'm writing, I'm able to increase the throughput and IOPS to my file system. And that's what we've just demonstrated here. So again, these are just some of the best practices that we would like to share with you when you start to use EFS. So if we go back to our file system or our presentation, these are some of the results that we did earlier. I ran this against a C5 large instance and recorded the results, our throughput test results. And you know, as we see here, a single thread running a 1 meg block size, we don't get great performance performance. Maybe we're able to get, in this example, we were getting 34 megabytes per second. I think in our example, we were getting around 25 megabytes a second. But as we increase the number of threads, or really a combination sometimes, increase the block size, reducing the number of sync operations to the file system, we're able to achieve high levels of throughput and really get up to roughly 250 megabytes per second throughput for these operations. Similar results with the IOPS test as well. So with a single-threaded IOPS test, it did take us some time. In this example, it was 16 seconds. I think in our example, it was just a little under 18 seconds. But as we added more threads, and we actually added more threads and wrote to different directories or subdirectories, we were able to dramatically improve the IOPS performance and get that duration to create 1,024 0-byte files down to very close to 1 second. So now that we've talked a little bit about, testing and optimizing your workload and the file system, let's talk a little bit about ingest. So when you're thinking about ingest, what do you typically think about? You think about, well, where's the data coming from? And how can I move it as fast and as easily as possible? So typically we see customers ingesting data into EFS from one of these 4 categories. First, it could be on-prem. Typically, this is a corporate data center. Second, it could be from maybe within your VPC. This could be from, from an existing EC2 instance that has an EBS volume attached. Third, it could be, a cloud service or some type of software appliance that you're running in the cloud. And the fourth could be from Amazon S3, our simple storage service. So one tool that we've recently released, we actually released this last year, very close to reInvent, is EFS File Sync. So EFS File Sync is a AWS management console utility that allows you to ingest data very quickly and very securely into an EFS file system. So it is very simple. As I said, it's a management console utility. You go into the console, you set up an agent, you launch an agent, set up an agent, launch a task, or create a task, and then run that task. That's really how simple and easy it is. Very fast. So we see it's up to 5 times faster using EFS File Sync than it is if you use your standard Linux copy tools. And it is secure. So the data is encrypted from your agent to the EFS service. So no need to actually have a VPC or a direct connect or a VPN connection because that data is encrypted in transit from the source where that agent is all the way to your file system. Now, there could be a time when you cannot use, or there's some reason where you can't use the EFS File Sync. So there are other tools out there, open source tools that you can use to ingest and move data into EFS. And what we want to do here is we want to quickly give you a demonstration of what those tools are and the level of performance you could expect when using some of these tools. So let's go back to this EC2 instance that I have running, and we'll go back to our script. So on this EC2 instance, I have an EBS volume, and this EBS volume has roughly 5 gigs of data, and the size of the data, each file is on average 1 meg. But it varies. So some of the files could be a couple of kilobytes, some of the files could be a couple of megabytes, but on average, they're 1 meg each. And we have 5,000 of these sitting on this EBS volume. And what we want to do, our task today is go ahead and copy this from this EBS volume to the EFS file system that's mounted on this instance. So the first tool we want to test is rsync. And if I asked most of you and said, what tool would you want to use if you wanted to copy data on Linux over to another file system? And a lot of people would probably say rsync. So if we go ahead and run this rsync command, first we want to go ahead and flush our cache. So we're starting fresh each time. I'm going to go ahead and use nload to monitor in real time the throughput to our file system. And if we take a look down here, our current throughput, we're roughly, say we're getting, it's hopping around because the size of the files differ so much. I'll say maybe on average 11 or 12 megabytes a second. So it's not great throughput. So I need to ask you, everyone here, so why is rsync, why is the throughput with rsync lower than expected? So I think one of the reasons, well, there's really two reasons. One of them is being that rsync is single threaded. So again, we have a single thread writing to EFS. Another one is that rsync is a very chatty tool. There's a lot of network operations, and we saw early with all of these network operations, because each network operation has latency associated with it, it can reduce, as a result, it can reduce the throughput we're able to achieve. So rsync is not a recommended tool when you're ingesting data into EFS and you're trying to do that as quickly as possible. So we went ahead and we just killed our rsync command there. I just want to make sure that everything looks good. Well, let's go on to the next one. So the next tool I think a lot of you would use would be just the Linux CP command. So let's go ahead and kick this off. Again, we're flushing our cache. We're dropping our cache. We want to make sure that everything is fresh. We're actually going from disk to EFS. And again, we'll try and load, and we'll monitor this real time. So we see that it definitely is better throughput than rsync, but it's not great. I would say maybe we're averaging 14, 15 megabytes per second throughput with this. Well, why is this slow as well? Well, what do we know about CP? Like rsync, it's single threaded. Now, it's not as chatty as rsync, so we get a little better throughput because there's not all these network operations going back and forth. But it is still single threaded, so we're not going to get great performance from CP. Let's just make sure that that is killed, and oops, we'll go ahead and move on. So this next command, it's just all I'm doing here is I'm creating a variable, and I want to set that variable to 4 threads per virtual CPU on this instance. And this is the threads variable that I'm going to use for my multi-threaded operations. So this next utility I'm going to use is called FP Sync, and FP Sync is a multi-threaded rsync. And if we kick this off, we'll use and load again, and we'll see that, you know, we went from what, 11 to 12 megabytes a second with rsync, a single-threaded rsync, to maybe the 30s, high 20s, low 30 megabytes per second. So definitely a big improvement over a single-threaded rsync, but still not great. And I think we can actually do better. But FP Sync is a very good tool if you need some of the functionality associated with rsync. So let's go ahead and kill this. We'll have to do this a couple of times, just make sure, because it does, oops, there we go. And everything is stopped, great. Let's keep moving on. So this next one is a parallel CP. So what we're gonna do is use new parallel and just the standard Linux CP command. So we went from maybe 15, 16 megabytes a second to in the 60s. So a big jump forward. So now, again, this is the same source, the same destination. The only thing we're changing here is the tool that we're using. And what we want to do is use a multi-threaded tool, and we want to use a less chatty network chatty tool. So here we're getting, you know, they're hopping around a lot, but I would say high 50s, 60s of megabytes per second. So let's go ahead and see if we can try to kill this. It's a little harder when you start spinning up so many different threads. And let's see how we're looking. And it looks like it's all cleared up. Okay, so this last one, it's actually, I'm gonna run this in stages. So this is a combination of FPART and CPIO. So is everyone familiar with CPIO? You know, there's some of you may have used CPIO for maybe archiving purposes. So what we're doing here is we actually used FPART to create a partition file. And a partition file looks something like this. It's really just, it's a file that lists all the different file system objects that we want to copy. So I'm just doing a head on the partition file. So this is basically the directory that we have, and these are all the some of the files and directories that we want to copy from source to destination. So with CPIO, there's actually 3 different modes for CPIO. There's copy in and copy out, but there's a third one that some of you may not be familiar with called copy pass. And with copy pass, what that allows us to do is to pass it a partition file, basically this index file that lists all of the source file system objects we want to copy. And that combined with new parallel, we will actually split that up into multiple threads, multiple domains, and run this in parallel. So with this last command, this will actually do the copy. And if we hop over and take a look at the performance we're able to get, now we're in the hundreds of megabytes. So roughly 100, say we're running average, maybe 130, 120, 130 megabytes per second throughput to EFS. And if we sit here and wait a few minutes, or actually just a few seconds, we'll see that it's only going to take us just seconds to copy 5 gigs of data. And again, this data set is a large number, 5,000 small objects, averaging in size of 1 meg each, anywhere from a couple of kilobytes to a couple of megabytes. But we can do all of that in only 39 seconds from EBS to EFS. So again, what we want to do is what I'm demonstrating here is you want to use the best tool for the job. So you want to use a multi-threaded tool that doesn't have a lot of network operations, that is less chatty on the network side, and it's very efficient. So the tool that you can find, the tools that I've tested out here, FPART, CPIO, and new parallel, I feel is a great combination to ingest a lot of data really fast in the EFS if for some reason you can't use the EFS file sync. So this is just a recap or a summary of the results that we just went through. Definitely you see that we had poor performance with rsync, but we had the best performance when we used FPART, CPIO, and new parallel. And again, this is just another some other results I ran earlier where we were able to get roughly 12 megabytes per second throughput with rsync, but in this example we were getting 122 megabytes per second on average to EFS. Same source, destination, same everything except for the tool we used. So again, we want to use the best practice is use a multi-threaded tool that is less chatty, that doesn't have a lot of network operations going on. So when we're running EFS, what do you need to do? So you know what? There's really not much. You definitely can view some of the file system metrics in terms of some of the API calls that are being issued to manage the file system on the administrative side, as well as some of the CloudWatch metrics to see how is your application driving, how is it using EFS, and then you can also perform backups. So as I mentioned, the API calls are logged using CloudTrail. So all of that is available in the S3 bucket associated with CloudTrail that you've set up. And all of these API calls are going to be coming from the console, the SDKs, as well as the CLI. We do have 8 CloudWatch metrics available to each file system to provide more insight into how the file system is behaving and how hard your application is actually driving that file system. Now, I did write a CloudFormation template that creates a CloudWatch dashboard that uses a function that we just launched early this year in CloudWatch called metric math. So now with this dashboard, you're actually able to see the throughput of your file system in megabytes per second. So it makes it very easy to see how your application is driving the file system in real-time results. So I do recommend going out to my GitHub repo, taking a look at the monitoring section, and in that section you'll see a CloudFormation template that you can go ahead and download. You can run it yourself, put in the file system ID, and within a matter of seconds you have this dashboard that you can use to monitor your file system, or you can make any changes to that CloudFormation template and those dashboards and customize it to your needs. In terms of backing up the file system, so we do have EFS backup solution, which allows you to back up an EFS file system to another EFS file system within the same region. It is a solution that you launch using a CloudFormation template. We stand up all the infrastructure that you need in order to do this. You would set the time, basically the schedule of when you want this backup to occur, and then we would manage the resources to go ahead and spin that up and make that backup for you. So again, that is out there. Just do a quick search for EFS to EFS backup solution, and you'll get access to that. So let's go ahead and wrap up really quickly. So some of the best practices we have: start out with general purpose performance mode file systems. That is our default, and that is the recommended. Start out with bursting throughput mode as well. And if you see that you need to move or transition or switch over to a provision throughput mode file system, then you can do that at pretty much any time. We do recommend Linux kernel 4 and above, and mounting using the EFS mount helper. But more importantly, you really want to mount using NFS of 4.1 and our recommended mount options. Try to aggregate your I/O. If you have larger I/O size, you're able to achieve higher levels of throughput. Use multiple threads. Take advantage of this parallel file system that you have behind you and access that file system using multiple threads. On top of that, use multiple instances. So if each instance has multiple threads access this file system and you have multiple instances, then wow, you're really going to be able to drive high levels of throughput to EFS. And when you're writing to that file system, if you need to write, try to write to different subdirectories. Don't write, millions and millions of file system objects into a same directory. See if you can design the application to write to multiple subdirectories so you can avoid inode contention and just get better performance. And then monitor your file system, use that CloudWatch dashboard and see how your application is driving that file system. There are a number of resources available on our EFS page at aws.amazon.com, and we have blog posts and white papers, reference architectures depending on the different application or workloads you may be running. We may have a reference architecture for you, some tutorials, and definitely some documentation out there. I do want you to go ahead and take a look at our tutorial on GitHub as well. There's a number of sections in that tutorial, and with CloudFormation templates and step-by-step guides, all the commands I ran today are actually in these tutorials, so you can go ahead and look at those and run them yourself in your environment to see how it performs. So that is it. What we want to do now is take some time and see if there's any questions that I can answer.